Exercise 18.9 is really just asking us to draw a frost circle and to see how we can use that to predict the stability of a molecule. Let's just read it together. It says the cyclopropenyl cation has a three-membered ring that contains a continuous system of overlapping p orbitals. Now, up till now, you've just seen the p orbitals in pi bonds. This is a good place to note that if you have a carbocation, that's really an empty p orbital. And hopefully that makes sense because you know that carbocations are sp2 hybridized because they're trigonal planar. Hybridization goes hand in hand with shape. So it's trigonal planar, so it's sp2 hybridized, and that means it has that one p orbital that it's not using. That's an empty p orbital. So positive charges are an empty p orbital. So in this case, you have that continuous system of overlapping p orbitals all the way around the ring. So next, it says this system contains a total of 2 pi electrons. Those are the 2 electrons in that pi bond. Now, you might recognize that that is the very first Huckel's number. And so you might think immediately this is probably aromatic, really stable, even though it has a positive charge. But we want to investigate that not using the pattern of Huckel's numbers, but using a frost circle. They want us to draw an energy diagram that shows the relative energy levels of the 3 molecular orbitals and predict, using that, whether the cation is expected to be really stable, aromatic, or not. So we saw in a previous video on the concept of aromaticity, we saw how the stability of aromatic molecules is really coming from their molecular orbitals. And you can predict the energies of the different wave patterns of the molecular orbitals by doing a little shorthand, and that's drawing these frost circles. So the first step is just to draw a circle. Now once you have the circle, take the shape of the molecule that you have, so here a triangle, and always put a point at the bottom. And then draw in the shape into the circle. Each one of the places where the shape hits the circle represent a molecular orbital with a certain amount of energy. So if you were to draw the molecular orbitals out, if you were to look at all the wave patterns this can move in, you would see that this ring has 3 possible wave patterns. And one of them is lower in energy, and 2 of them are higher in energy, but they have the same energy as each other. So here we know we have 2 pi electrons, the 2 electrons in the pi bond. Notice this positive charge, that's an empty p orbital, there are no electrons there. It wouldn't make sense for electrons to have a positive charge. So we're going to fill those 2 pi electrons, we'll fill those in our orbitals. We have 1, 2. We filled in our lowest molecular orbital. Notice that all of the electrons are paired, and notice they're all in the lowest energy possible orbital. So it's that pairing and stabilization that makes this molecule aromatic. Here you can sort of visualize qualitatively the molecular orbitals. You can get a sense of the energy of them. And you can see that all the electrons are paired up, so they're not going to be as reactive, and they're paired up in a low energy orbital, and that's what makes the molecule as a whole aromatic, even though it has a positive charge. So in this example, we drew a frost circle, that's this yellow circle, with the shape of the molecule inscribed in it, where each of the points that hit the circle represent a molecular orbital with a certain amount of energy. And we filled in the electrons in p orbitals in the molecule. And we used that to determine whether the molecule as a whole was really stable, aromatic, or really unstable, anti-aromatic. Notice that if you didn't have the positive charge, let's say instead of a positive charge, you had a lone pair with like a negative charge. Lone pairs also exist in p orbitals, so you could have that parallel p orbital there. So you'd have a continuous system in a ring. But in that case, you would have 4 pi electrons. So if you filled those in, you would have 2 unpaired electrons, and the molecule would be anti-aromatic. That's if you had a lone pair there. We didn't. We had a positive charge, so you didn't have those extra 2 electrons, and so the molecule was aromatic. So that should give you a sense of how you can use those frost circles to predict the aromaticity or anti-aromaticity of a conjugated ring.